Mitsubishi Chemical Corporation. My title is Accelerating Materials Discovery with Quantum Computing. Our company is heavily focused on DX promotion recently, and quantum computing is a next generation paradigm shift or necessary technology for that. And this is why we are really focused on R&D of quantum computing. So it's mainly R&D right now, but value chain, sales, procurement, manufacturing, logistics, we want to apply quantum computing in all of these different areas. And we participated in the initiative with IBM Q Hub and Keio University, or at Keio University. Keio Q Hub used IBM Cloud, and this was the only location that we could access that from Asia. And we had participation from Japan and also overseas. We also collaborated with IBM researchers. So this was a great location for building network. And in Q Hub, drug discovery, financial calculation, real time, machine learning, new material search, everything was done. MUFJ, G, and Mizuho were also other members. We now have Mitsui Trust Bank, Toyota, Hitachi, Sony, SoftBank. Total of 9 companies are part of this hub, and it's becoming even more active. From 2018, we started our joint research mostly with Keio and IBM in terms of quantum chemicals and optimization and AI in these main areas. As for quantum chemistry, lithium air battery, and also organic EL, excitation energy, and also tensor, Monte Carlo, quantum algorithm development, to cite some of them. And in terms of optimization, isotope, material search, photochromic material search, and for AI, classification, as well as reservoir learning of sequential data. I would like to talk about specifically 2 use cases later on. In addition to Q-Hub, in 2019, Qnesis, a startup, started joint research with us. This is mostly about organic photo materials, optical materials. So high precision optical material property calculation, which could not be solved with a classical computer, mostly focusing on NISQ application. So Qnesis, IBM, Osaka University, and ETH in Switzerland worked together to develop a methodology of property prediction for oscillator, as well as a excitation state reaction calculation method, including azobenzene, and we have issued written papers together. And last year, we had a huge inflection point for our company. So different startup companies and also national projects, we have participated in many of them and started to promote the research even more strongly. This is one example, joint research with Fujitsu. So this is the domestic quantum computer, much anticipated. We want to activate the quantum computing industry. So new material development is one, but also drug discovery is another area we are collaborating with Fujitsu. Fujitsu is, of course, focusing on quantum computing, but also Fujitsu has been building a strong track record in terms of drug discovery, so we have decided to work together. Other than that, in the beginning of this year, together with Psi Quantum MFUG, we have announced a partnership for joint research of a quantum computer. FTQC is a focus. We want to be ready for the era of FTQC. We don't want to lag behind, and that's why we have started the research. Energy efficiency related material is a focus. Once we can realize this, we should be able to contribute to addressing the climate problem. And last year, so SIP, this was Cabinet Office-led initiative involving various universities and companies, and we joined this initiative. So this is a tripartite cooperation, a national project. Most of the co-projects were base research, but SIP is actually inclusive of commercialization. And we conduct joint research here, and finally, we want to turn this into real business. Now, for SIP, QC and quantum sensor, sensing and platform, these are the different pillars, and we are participating in the quantum computing part. So the representative researcher is from AIST, and we are promoting the research on quantum computing. As for SIC, classical quantum material improvement method is our focus. So material informatics and the classical methodology from Toronto University, we have Professor Allen, and also Keio University, Mitsubishi Chemical, we are all working together. In the end, what we want to achieve is being able to simulate using QC, and based on data in the database, we can use that for teaching and developing new materials. We want to feed this back to the actual space and run this cycle to accelerate the development of materials so that we can achieve carbon neutral society. So there are two different categories. One is a sequential issue, and the other one is an inverse problem. One starts from the structure and then lead it to the performance, and the other one is, of course, the reverse. We have been doing the sequential problem solving in the past, but when we convert it, this means that we have to turn chicken soup into chicken. So this is how challenging this is. And I would like to talk about these two ways of methodology, and I would like to show you some cases. Now, for the sequential issue, we have OLED emitter, TADF. If you want to use OLED in display, green, blue, and red, three different colors are needed. High level of emittance and efficiency is necessary. And the green and red have achieved the target, but blue efficiency is still very low. So we are now focused on TADF, which is featured in Nature. This is the next generation material for emitter. So triplet excitation and singlet, and the difference between the two delta EST is very small. So for blue, theoretically, 100% emitter efficiency could be achieved theoretically. And delta EST value is very important, and we want to be able to calculate the correlation between the experimental value versus the simulated value. And we are working with Georgia Tech, and we have formulated 3 different materials to calculate the delta ES.
In calculating delta ES, there's ground state and excited state that have to be calculated. And for ground state, VQE method is used for calculation, and using the result of calculation, the the excited state is calculated, there are two methods there. First, the QEOM method. So VQE, the ground state, is used as the base, and classical linear response is used as the framework, and within that, the calculation is made. The second approach is VQD approach. This is an advanced approach of VQE. So the overlap between the ground state and the excited state is optimized to come to the excited state. By using these two methods with simulator, that delta ES was calculated to compare against experiment value. So there was a correlation identified, and algorithm here seems to be used. It seems usable. And however, using the actual machine, due to the impact of noise for both methods, we didn't identify correlation. So together with IBM and Keio University, we came up with an error separation method. Then using the error mitigation method, as you see in the purple light, we could identify correlation. So algorithm combined with error mitigation will turn the quantum computer usable to a certain extent. And as a result, with IBM, Keio, and JSL, we made a joint publishing, and we've published jointly the paper. And this is about the direct pollution. And next, what I would like to talk about is the example of inverse problem. The target is ALQ3, which is UKEL light emitter, and within light emitter there are 3 H atoms. So by replacing it with the isotopic D atom, then there is experiment that shows that the non-radiation speed is suppressed and then quantum yield is improved. So in all the combination of H and D, the highest efficiency light emitting a pattern is pursued. And to pursue or search for the highest efficiency, we came up with the method QL. And the gamma and the beta. And then expected value is estimated, and by updating gamma, and we came up with an appropriate optimum phi value. And for your information, the phi here, by changing it to heuristic, to calculate this with QLA, it has to go down to Ising Hamiltonian. To do so, the quantum chemistry and machine learning were used to create Ising Hamiltonian. And with Ising Hamiltonian on quantum computer, optimum structure was searched. And the result is this. Firstly, Ising Hamiltonian, to what extent can we construct it with accuracy? And quantum technology, quantum training data has been increased gradually. And when it goes to 13, then we could reproduce completely. So compared to 64, so if part of the data is used, then performance was estimated. And next, using VQC and QA, whether we can conduct a similar search, we did some simulation. There are two patterns we calculated. The first is the search for high efficient one, and the other one is synthetic cost was considered as well. As we saw, if a search is doable, and as a result, for VQE, exact answer was arrived at. So material was searched at 100%. QOA, 100% reproduction was not possible. However, we could see the convergence to the precise answer. Next, we used the actual machine to do calculation. So this is the result. Using the simulator, then there's convergence here. But using the actual machine, then there's a variance identified. So this is a quantum circuit that was used for calculation. It's long here, as you can see here. And using the circuit noise affects and the divergence emerges. So the result of calculation here, or probability, is low here. And I will not go into the details of methodology, but together with IBM and Keio University, RQAOA method was invited together with them. RQA and RPVE methods were identified, rather. They invented. And 1, 2, 3, 4, there are 6 qubits here. So QAOA, VQA calculation identify or determine 6 values all at once. Then, but there is impact of noise. But the RPVE method the value is determined from qubit with strong noise. So by making determination one by one, calculation result will be a reasonable one. That's our estimation. And as we calculated RPVE, the QAOA and VQE combined, then we observed convergence into the precise answer. So by sequentially determining qubit value, we saw the convergence into the appropriate or favorable level. So this is a summary. Eventually, our firm Mitsubishi IBM worked together last year and in producing the paper of the accomplishment. And this is my observation. At our firm, we have focused our research on IBM Q Hub. The benefit is the ability to use actual machine. And by accumulating the experiments, we are readying ourselves to accumulating use cases. And in Q Hub, there are interdisciplinary experts. So there's good environment for research. And through collaboration with Keio and IBM, more than I expected, we could conduct various experiments. And we validated use case in the area of optimization, quantum AI, and quantum chemistry. In the future, in the near-term future, hopefully, quantum computer has the potential to replace the classical computer. And so far, toward the practical realization of NISQs, we have conducted research. Of course, calculation algorithm needs to be prepared, but error mitigation method needs to be developed as well. Also, quantum computer is something that needs to be addressed with a long-term view, and so that we will not be left behind other countries. We like to continue with our efforts. Thank you. Thank you for listening.